PM 2.5 refers to extremely fine airborne particles that are roughly 30 times smaller than the width of a human hair. This makes them invisible to the naked eye and easily inhalable into the human respiratory system. Due to their tiny size, these particles can remain suspended in the atmosphere for extended periods of time and travel long distances from their original sources, allowing them to impact air quality and human health in both urban and rural areas. Examples of this can be black carbon, trace metals, and organic compounds. Climate change worsens air pollution by increasing the frequency and the intensity of conditions that generate or trap PM 2.5. Conditions such as prolonged heat waves, stagnant air masses, and large scale wildfires can release vast amounts of fine particulate matter into the atmosphere. These impacts are expected to intensify in Southeastern Europe, where PM 2.5 is especially concerning because these conditions have a strong warming effect and a long atmospheric lifetime, allowing it to persist in the air and amplify both climate change and long-term health risks. Southeastern Europe, consisting of countries like Bulgaria, Romania, Greece, Croatia, Serbia, Hungary, and many other countries, consistently experience higher PM 2.5 concentrations than in Western Europe, primarily due to geological factors and a reliance on unsustainable energy sources. Importantly, pollution is not limited to urban centers. Regional background levels remain high throughout the entire year. Long-term exposure to PM 2.5 is responsible for a large number of premature deaths throughout Europe. Southeastern Europe bears a disproportionate share of this burden due to persistently high pollution levels from coal power, residential heating, traffic, and a large industry. Most of these premature deaths are linked to heart disease, stroke, lung conditions, and cancer. This highlights the severe public health consequences of air pollution in the region. Primary sources of particulate matter emissions in Europe include coal-based energy production, residential heating, manufacturing and extractive industries, and transportation, all of which release significant amounts of fine particles into the atmosphere. Together, these sectors contribute heavily to PM 2.5 pollution, affecting air quality across both urban and rural regions and posing serious risks to human health and the environment. Coal-fired power plants continue to play a central role in electricity generation throughout much of southeastern Europe, despite their age and inefficiency. Many of these facilities are outdated and release large quantities of PM 2.5, along with other gases that contribute significantly to both air pollution and climate change. This pollution poses serious environmental and health challenges throughout the entire region. Residential heating is among one of the most significant sources of PM 2.5 in the region. Areas with no or very unreliable energy sources compel many households to depend on solid fuels such as wood and coal just to heat their own homes. This reliance results in severe seasonal pollution, particularly during the colder months when heating demands are at their highest. This exacerbates air quality issues and health risks. Southeastern Europe's large industrial activities are a major contributor to PM2.5 pollution, releasing fine particles through manufacturing processes, energy use, and material handling, especially in industries such as cement, metal, mining, and chemical industries. These emissions are often highly localized, disproportionately affecting the nearby communities. This is especially a concern in areas where regulatory oversight and enforcement are extremely limited. Transport related emissions are also a significant source of PM2.5 pollution in urban areas, areas where aging vehicle fleets, a large percentage of diesel engines, and heavy traffic congestion is common. This contributes to continuous particle release from things like your own brakes and tires, or more irresponsible sources like rolling coal from a diesel engine. As a result, city residents experience prolonged exposure to harmful air pollutants. This poses serious health risks over time, especially for those who live in the big city.
As stated earlier, PM 2.5 refers to fine particulate matter with a diameter of 2.5 micrometers or smaller. So because of their small size, these particles can penetrate deep into the lungs and even enter the bloodstream, allowing them to affect multiple organ systems. In Southeast Europe, exposure to PM 2.5 is driven largely by combustion-related sources. Residential heating, especially the use of biomass and coal, remains widespread, particularly in rural and low-income areas. Road transport, including both exhaust emissions and non-exhaust sources, such as brake and tire wear, also contribute substantially. Industrial activities and coal-fired power generation further compound exposure. So what distinguishes Southeast Europe from other regions is the persistence of these exposure pathways. PM 2.5 concentrations frequently exceed the World Health Organization guideline levels, and exposure occurs not as isolated events, but as chronic long-term condition affecting entire populations. Short-term exposure to PM 2.5 has been consistently linked to acute health effects, particularly increases in daily mortality. Studies examining day-to-day fluctuations in air pollution show that even brief spikes in PM 2.5 concentrations can trigger adverse outcomes. So, research analyzing hundreds of cities worldwide demonstrates that increases in PM 2.5 are associated with elevated all-cause mortality within the same day or the following day. These short-term effects are especially pronounced for cardiovascular events, such as heart attacks or sudden cardiac events. The key takeaway here is that PM 2.5 does not need years to cause harm. Acute exposure acts as a physiological stressor that can trigger fatal events, particularly among vulnerable populations, such as older adults or individuals with pre-existing heart or lung disease. In Southeast Europe, where baseline exposure levels are already high, these short-term risks are layered on top of chronic exposure, compounding overall health impacts. While short-term effects are concerning, the most substantial health burden from PM 2.5 comes from long-term exposure. Large cohort studies across Europe consistently show that sustained exposure to PM 2.5 increases the risk of premature death and years of life lost. One critical finding from European cohort analyses is that elevated mortality risk persists even at relatively low concentrations of PM 2.5. So, in other words, there's no clearly defined safe threshold below which PM 2.5 exposure poses no risk. This has major implications for Southeast Europe, where average concentrations often remain well above recommended levels. Long-term exposure contributes to cumulative physiological damage, including chronic inflammation and progressive disease development. So as a result, PM 2.5 is now recognized as one of the leading environmental determinants of premature mortality across Europe, with Southeast European countries experiencing disproportionately high burdens per capita. Cardiovascular disease represents one of the most well-established and severe health outcomes associated with PM 2.5 exposure. Long-term exposure increases the risk of ischemic heart disease, stroke, and other cardiovascular conditions. The biological mechanisms underlying these associations are increasingly well understood. Fine particles promote systemic inflammation and oxidative stress, impair vascular function, and continue to atherosclerosis. Over time, this accelerates cardiovascular disease progression and increases the likelihood of acute events. Important to note, individuals with pre-existing cardiovascular conditions are particularly vulnerable. In Southeast Europe, where rates of cardiovascular disease are already elevated due to demographic and lifestyle factors, PM 2.5 exposure acts as an additional and significant risk amplifier. Not all PM 2.5 is equally harmful, and this slide highlights why particle composition matters. So research shows that particles originating from combustion sources, especially residential fuel burning and traffic, exhibit higher oxidative potential than other types of particulate matter. So oxidative potential refers to a particle's ability to generate reactive oxygen species in the body, which can damage cells and tissues. Particles rich in black carbon and organic compounds are particularly effective at inducing oxidative stress, which in turn drives inflammation and disease development. This distinction is especially relevant for Southeast Europe, where residential biomass burning and traffic emissions dominate PM 2.5 composition. Even if mass concentrations are similar to those in other regions, the chemical makeup of particles can lead to greater health impacts. This helps explain why populations exposed to similar PM 2.5 levels may experience different disease burdens, just depending on emission sources. Accurately assessing exposure is essential for understanding health risks, and recent research highlights important limitations in traditional exposure models. Many studies estimate exposure based solely on residential location, assuming individuals spend most of their time in the home. However, mobility integrated exposure assessments, those that account for daily movement, such as like commuting and occupational activities, often reveal higher cumulative exposures. This suggests that residential-only models may underestimate long-term health risks, particularly in urban or highly mobile populations. So in Southeast Europe, where individuals may experience significant exposure during commuting or work-related activities, this underestimation could obscure the true magnitude of PM 2.5 related health impacts. Improved exposure assessment strengthens the evidence linking PM 2.5 to both mortality and cardiovascular morbidity. Altogether, this evidence highlights PM 2.5 as a major and preventable public health threat in Southeast Europe. The most effective interventions or changes are those that target dominant exposure sources, particularly residential solid fuel combustion and traffic emissions. Transitioning to cleaner household energy, improving transportation systems, and reducing reliance on high-emission fuels could yield substantial health benefits. And importantly, these interventions would disproportionately benefit vulnerable populations who bear the greatest exposure burden. In fact, evidence from recent source-specific PM 2.5 mortality research in China, as pictured, demonstrates the health benefits of reducing emissions from transportation and residential combustion sources. And although the study was conducted in China, the underlying health mechanisms are consistent with European cohort studies and fairly applicable to Southeast Europe. The overarching message here is that reducing PM 2.5 exposure is not only an environmental priority, but a critical public health strategy. Addressing chronic exposure pathways in Southeast Europe has the potential to prevent thousands of premature deaths and significantly reduce the burden of cardiovascular and respiratory disease.
This presentation focuses on fine particulate matter known as PM 2.5 and its role in air pollution, climate change, and public health. PM 2.5 is one of the most harmful air pollutants because it penetrates deep into the lungs and bloodstream. We focus on Southeastern Europe because this region experiences persistently high exposure levels and disproportionate health impacts. This slide explains why PM 2.5 pollution matters from a pollution level perspective by quantifying its overall burden on society. The impacts of PM 2.5 extend beyond individual health outcomes and intersect with climate change, public health systems, and social equity. The Global Burden of Disease study provides a standardized way to measure this impact using two key metrics: PM 2.5 attritable mortality and disability adjusted life years, or DAILYs. DAILYs combine years of life loss, PM 2.5 related deaths, with years lived with illness or disability, offering a comprehensive picture of total health loss. According to GBD estimates, PM 2.5 is responsible for a substantial number of premature deaths each year, primarily due to cardiovascular disease. These deaths translate into millions of DAILYs lost globally, making air pollution one of the leading environmental risk factors worldwide. Importantly, this burn is not evenly distributed. Southeastern Europe experiences a disproportionately high share of PM 2.5 attritable mortality and DAILYs compared to Western Europe. This reflects long-term exposure, higher reliance on fossil fuels, older infrastructure, and socioeconomic vulnerabilities. Quantifying the burn in this way highlights that PM 2.5 pollution is not only an environmental issue, but also a major public health and equity concern, reinforcing the need for stronger air quality and climate policies. Southeastern Europe was selected because PM 2.5 exposure is consistently higher here than in Western Europe. This is not due to short-term pollution events, but long-standing structural factors such as energy systems, housing, and transportation infrastructure. This slide highlights the main sources of PM 2.5 pollution, contributing to elevated exposure levels in Southeastern Europe. As shown on the map, regions with higher PM 2.5 concentrations strongly overlap with areas that rely heavily on coal-based power generation and residential solid fuel heating. According to the European Environment Agency, coal remains a major energy source in several southeastern European countries, contributing substantially to fine particulate emissions. In addition, many households rely on wood and coal for residential heating, particularly in colder months, which produces high levels of PM 2.5 at the community level. Transportation is another important contributor. Aging vehicle fleets and limited emissions controls increase particulate emissions compared to newer fleets in Western Europe. Industrial and manufacturing activities further add to the regional pollution burden, especially where environmental controls are less stringent or outdated. These pollution sources are not temporary or isolated. They are embedded in regional energy systems, housing infrastructure, and transportation networks. As a result, PM 2.5 exposure in Southeastern Europe is chronic rather than episodic, contributing to long-term public health risks. Evidence from long-term cohort studies confirms that sustained exposure to PM 2.5 from these sources increases natural cause mortality even at concentrations below existing regulatory limits. Air pollution refers to the presence of harmful substances in the atmosphere that poses risk to human health and the environment. Major air pollutants include fine particulate matter known as PM 2.5, nitrogen oxides or NOx, sulfur dioxide, and ground level ozone. Among these pollutants, PM 2.5 is considered the most harmful to human health. These particles are small enough to bypass the body's natural defenses, penetrate deep into the lungs, and enter the bloodstream, where they can affect multiple organ systems. According to the World Health Organization, long-term exposure to PM 2.5 significantly increases the risk of cardiovascular diseases, respiratory illness, lung cancer, and premature death. Importantly, cardiovascular diseases accounts for a large portion of PM 2.5 related mortality, which expands the health impacts of air pollution beyond traditional respiratory concerns. Evidence from large European cohort studies, including the ESCAPE project published in the Lancet, confirms that increased mortality occurs even at PM 2.5 concentrations below current regulatory limits. Global burden of disease estimates further demonstrate that PM 2.5 is a leading environmental risk factor worldwide, contributing to millions of deaths annually. Because of its widespread sources and severe health impacts, PM 2.5 plays a central role in both air quality management and climate-related policy discussions. This slide explains the connection between PM 2.5 air pollution and climate change. A key component of PM 2.5 is black carbon, which is produced through incomplete combustion of fossil fuels, particularly from coal-based power generation, diesel engines, and residential solid fuel heating. Black carbon is important from a climate perspective because it absorbs solar radiation and contributes to atmospheric warming. Unlike long-lived greenhouse gases, black carbon remains in the atmosphere for a relatively short time, but it also has a strong warming effect while present. When deposited on snow and ice, it also reduces surface reflectivity, accelerating melting. Many of the same sources that emit PM 2.5, such as fossil fuel combustion for energy and transportation, are also major contributors to climate change. This means that policies aimed at reducing PM 2.5 emissions can deliver immediate public health benefits while also contributing to climate mitigation. Evidence summarized by the European Environment Agency and the World Health Organization emphasizes that reducing fine particulate pollution represents a critical co-benefit strategy, addressing air quality, climate change, and environmental justice simultaneously. A critical finding from the scientific literature is that there is no safe exposure level for PM 2.5. According to the World Health Organization, extensive epidemiology evidence shows that adverse health effects occur even at low concentrations of fine particulate matter. This means that there is no threshold below which PM 2.5 exposure can be considered harmless. Health risks increase continuously as concentrations rise, but importantly, measurable impacts occur even at levels well below many national and regional air quality standards. Long-term cohort studies, including the ESCAPE project published in the Lancet, confirmed that increased natural cause mortality occurs at PM 2.5 concentrations below current European legal limits. These findings demonstrate that regulatory compliance does not necessarily equate to health protection. Global burden of disease estimates further support this conclusion by showing that PM 2.5 contributes substantially to premature mortality and disease burden across populations, even in regions that meet existing air quality standards. Together, this evidence highlights a fundamental gap between health-based science and regulatory policy, reinforcing the need for more protective air quality guidelines and stronger emissions control. This slide summarizes the major sources of air pollution, with particular emphasis on those that contribute mostly significantly to PM 2.5 emissions. Across Europe, the primary sources include energy production, transportation, industrial activity, and residential heating. Fossil fuel-based energy production, especially coal-fired power generation, is a major contributor to fine particulate emissions. Transportation sources included road traffic and diesel-powered vehicles release both primary PM 2.5 and precursor pollutants that form fine particles in the atmosphere. Industrial and manufacturing activities further add to PM 2.5 levels through combustion processes and material handling. In addition, residential heating, particularly the use of coal and wood in household stoves and boilers, plays a significant role in local and regional air pollution, especially during colder months. Evidence from the European Environment Agency shows that these sources are deeply embedded in economic and infrastructure systems, particularly in Southeastern Europe. As a result, PM 2.5 exposure is chronic rather than episodic. The World Health Organization and Global Burden of Disease study both emphasize that emissions from these sectors contribute substantially to long-term health risks, even at relatively low ambient concentrations. This slide highlights the strength of the scientific evidence linking PM 2.5 exposure to adverse health outcomes. Much of the evidence comes from large, long-term cohort studies that follow pollutions over many years, allowing researchers to assess chronic exposure rather than short-term effects. One of the most influential examples is the ESCAPE project. Published in The Lancet, the multi-country European study found that long-term exposure to PM 2.5 is associated with increased natural cause mortality. Even at concentrations below current European legal air quality limits, these findings are especially important because they demonstrate that health risks persist even where regulatory standards are met. The study relied on robust exposure modeling techniques, including land use regression models that combine air monitoring data with spatial and environmental variables to estimate long-term exposure at the population level. The World Health Organization and the Global Burden of Disease study both draw on this body of evidence to conclude that PM 2.5 is a leading environmental risk factor globally. Together, these studies provide strong, consistent, and scientifically credible evidence that long-term PM 2.5 exposure poses serious health risks and warrants more protective air quality policies. This slide summarizes the major health impact associated with long-term exposure to PM 2.5. The strongest and most consistent evidence links PM 2.5 exposure to cardiovascular diseases, respiratory illnesses, and premature death. According to the World Health Organization, cardiovascular disease accounts for a large portion of PM 2.5 related mortality. Fine particles enter the bloodstream, triggering systematic inflammation, oxidative stress, and changes in blood vessel function that increase the risk of heart attacks and strokes. PM 2.5 exposure is also strongly associated with respiratory illness, including asthma, chronic obstructive pulmonary disease, and reduced lung function. Long-term exposure increases susceptibility to infections and worsens existing respiratory conditions. Importantly, these health impacts translate into premature mortality. Large cohort studies, including the ESCAPE project, demonstrates increased natural cause mortality even at PM 2.5 concentrations below current legal limits. Global burden of disease estimates further shows that PM 2.5 is one of the leading environmental risk factors contributing to early death worldwide. Together, this evidence reinforces that PM 2.5 is not only an environmental issue, but a major public health concern with widespread and measurable consequences. Southeastern Europe was selected because PM 2.5 exposure is consistently higher here than in Western Europe. This is not due to short-term pollution events, but long-standing structural factors such as energy systems, housing, and transportation infrastructure. This slide explains why PM 2.5 pollution matters from a pollution level perspective by quantifying its overall burden on society. The impacts of PM 2.5 extend beyond individual health outcomes and intersect with climate change, public health systems, and social equity. The Global Burden of Disease study provides a standardized way to measure this impact using two key metrics: PM 2.5 attritable mortality and disability adjusted life years, or DAILYs. DAILYs combine years of life loss, PM 2.5 related deaths, with years lived with illness or disability, offering a comprehensive picture of total health loss. According to GBD estimates, PM 2.5 is responsible for a substantial number of premature deaths each year, primarily due to cardiovascular disease. These deaths translate into millions of DAILYs lost globally, making air pollution one of the leading environmental risk factors worldwide. Importantly, this burden is not evenly distributed. Southeastern Europe experiences a disproportionately high share of PM 2.5 attritable mortality and DAILYs compared to Western Europe. This reflects long-term exposure, higher reliance on fossil fuels, older infrastructure, and socioeconomic vulnerabilities. Quantifying the burden in this way highlights that PM 2.5 pollution is not only an environmental issue, but also a major public health and equity concern, reinforcing the need for stronger air quality and climate policies. In conclusion, this presentation demonstrates that reducing air pollution, particularly PM 2.5, offers significant and overlapping benefits for climate mitigation and public health. Because PM 2.5 and greenhouse gases often originate from the same sources, such as fossil fuels combustions, policies that reduce air pollution can simultaneously reduce climate warming emissions. The scientific evidence reviewed throughout this presentation clearly shows a gap between health-based guidelines and current legal air quality standards. The World Health Organization has concluded that there is no safe level of PM 2.5 exposure, yet many existing regulatory limits remain less protective than what the science recommends. Reducing PM 2.5 emission also provides important air pollution, climate co-benefits, lower emissions of black carbon and other combustion-related pollutants can lead to immediate health improvements while contributing to near-term climate benefits. Finally, the disproportionate burden of PM 2.5 exposure in Southeastern Europe highlights critical equity concerns. Long-term exposure, older infrastructure, and reliance on fossil fuels place certain populations at higher risk. Taken together, these findings underscore the need for stronger, science-based air quality policies that align with health evidence, address regional disparities, and recognize air pollution control as a key strategy for protecting both human health and the climate.